Hello, and welcome to Astronomy 100. In this video, we're going to continue our discussion of stellar evolution. And in our last video, we talked about how intermediate mass stars, stars that are greater than half the mass of the Sun and less than 8 times the mass of the Sun, intermediate mass stars, we talked about how they end their main sequence life and how they ultimately end their existence by going through a few changes at the core of the star. Now, a couple of key facts to remember is remember that for a star that's an intermediate mass star, it develops a carbon core, but to get that carbon to fuse into the next element, it needs the core to reach a temperature of 600 million kelvins. To get that to happen, gravity has to compress the core to make it hot enough to get the carbon to fuse. But the problem with an intermediate mass star is if it's less than 8 solar masses, then the mass, and hence the gravity, is not powerful enough to get that core small enough to reach that magic 600 million Kelvin temperature. So what the star does is it puffs off its outer envelope through a series of pulsations, puffing off more and more material each time, and it leaves behind a white dwarf, which is the remnant core of what used to be that star. Now, what we're going to talk about in this video are some of the details that go with planetary nebulae as well as white dwarfs. So let's go ahead and get started. Here's a sampling of 6 different planetary nebulae. And there are literally hundreds of these that you could see on any given night. If you have a telescope and you have the ability to go outside and look to find these, again, there are hundreds of them. But I have a sample of about 6 of them here just to show you some of the interesting differences in the details. Remember, each one of these started out as an intermediate mass star, like the Sun, and has, through a series of pulsations, has puffed off its outer envelope. Notice that each one is a cloud that surrounds a white dwarf. Notice the little tiny white dot at the center of each and every one of these. So this is the white dwarf, which is the core, the remnant core of what used to be a normal star. Now, the planetary nebula, this is the cloud that is getting steadily bigger and bigger as time goes by. If we could take a picture of each of these tonight and then come back in, 50 years and take another picture, they would be noticeably larger. So these clouds are expanding. And you'll notice the shapes of each one is slightly different compared to the others. There's a lot of dynamics that goes into what causes the shape, and it's a topic that's just a bit more than what we have time for. But what I want you to notice in a couple of these, notice you can actually see the different pulsation periods that have caused the envelope to expand. So notice this one looks like a bunch of circular rings that are nested inside of each other. Each of these circular shapes is a certain amount of material being pushed off over and over and over again. And that's why it looks like it's sort of a nested set of rings. So this star has pushed off all of its material. This one has the nickname, it's called the Cat's Eye Nebula, and it's just named after what a marble that's called a cat's eye would look like. It's an old idea. This one here I picked because you can actually see the filaments. You can see the stringers, or how the material, as it's getting bigger and bigger, pushed off into space, leaves behind all these filaments. You can see structure to the cloud as it gets pushed off. This one is fairly recent. You can see that it's just starting to expose the white dwarf at the center. This one is called the Snowball Nebula, and it's because it's very symmetrical. Notice how it's almost perfectly circular, spherical. If you could see this in space, although it looks like a circle, each one of these would be 3-dimensionally spherical, or pretty close to it. So from any angle looking at this, it would look the same. Think of it as like a bubble more than a circle. This one here, lots and lots of details to the clouds. This one here has a fairly politically incorrect name that's been around for a very long time. This one is called the Eskimo Nebula. And the reason why it is called the Eskimo Nebula is because of the appearance, or the way that it looks. It looks like a face that's inside of a furry hood. If you think about the Native Americans who live to the north, if they're wearing a hood that's made out of an animal skin or an animal fur, you often see pictures of them with these big furry hoods and their faces buried deep down inside. So that's the nickname, the Eskimo Nebula. But notice the different filaments that come with it. So this is a very detailed look of this star pushing off its outer envelope. So let's concentrate a little bit more on the white dwarf that you'll notice again at the center of each one of these 6 examples. The name white dwarf is appropriate. The reason why it's called that is because it is very hot and so therefore looks white in appearance, and it is very small, hence the name white dwarf. Now, to show you how big one of these white dwarfs are, let's compare it to the size of the Earth. So someday, the sun will expand and push off its outer envelope, and it will leave behind the remnant core, or a white dwarf. But notice the size of the core is approximately the size of our Earth. Now, the thing that you need to keep in mind, though, is this core of this star has been compressed many, many times to become the size that it is today. If it were the core of the sun today, it would be much bigger. But gravity has compressed and squeezed, causing the core to be steadily smaller and, of course, hotter. And by the time the envelope puffs off into space, we now expose the core. But remember, gravity doesn't go away. The force of gravity is continually squeezing this material, causing it to be highly compact. And so therefore, it is very small, hence the name white dwarf. Now, what do we know about white dwarf stars? Well, here are some of the details. The star itself, it's a bit of a misnomer because they are not active stars. These are dead remnants of what used to be the core of an intermediate mass star. So be careful with the terminology. A white dwarf star is not a star that is still actively doing what other stars do. But a white dwarf is composed mostly of carbon. And the reason why we know that is because if we can see the light coming from the star, then we can take the spectrum of that light and we can see the chemical fingerprint of carbon. So we know that they're mostly made out of carbon, and that should make sense because remember, carbon was the material that the star was not able to get to fuse. So the intermediate mass star turned its helium into carbon, but it could not get the carbon to fuse. So it should make sense that they're mostly made out of carbon. These are very, very hot. Their surface temperatures are 50,000 kelvins or more. But keep in mind, they're no longer actively producing energy. So there's no internal energy source, there's no nuclear fusion occurring. The nuclear engines of this star have died, have gone away. Why so hot? Well, it takes time to cool off. When you make something incredibly hot, it does not cool off overnight. It will literally take thousands of years for this thing to slowly dissipate all of its heat and slowly cool off. So by the time we get to see them, they're still very, very hot, even though they're not actively producing energy. As we saw on the last slide, gravity has shrunk them down to be about the size of the Earth, so they're highly compressed. They still have the mass of what used to be a normal stellar core, so their mass is still very, very big. There are lots and lots of material that has been crushed down to a very small size. And when you have a lot of material shrunk to the size of something like the Earth, that makes it very, very dense. The density of a white dwarf star is enormous. Just one little tiny spoonful of this material would weigh many, many hundreds of tons. So lots and lots of material packed into a very, very tiny volume. Now, to sort of put the whole thing together, if you remember from a previous video, we were going to slowly piece together this slide. And as we talked about each of the different masses of the stars and how they evolve, we were going to add another line. A couple of videos ago, we talked about how the low mass stars evolve and reach the point where they become black dwarfs. Now, we can add another line. Intermediate mass stars go through all of the same series of events, but notice the difference. An intermediate mass star can actually go further down the evolutionary sequence, successfully overcoming what a low mass star could not, but then eventually running into the problem of not getting the carbon to fuse, and so they die, producing a planetary nebula and a white dwarf. The main difference also, don't forget, is time. How long it takes for a low mass star to get to this point is very, very long. How long it takes an intermediate mass star to get to this point is much, much faster. The higher the mass of the star, the faster it evolves and goes through its evolutionary sequence. Now, in a future video, we will eventually talk about what do high mass stars do, and we'll get to that at some point. One last thing I want to show you. If we go back to the Hertzsprung-Russell diagram, this is again a diagram we've seen in some of our previous videos. The Hertzsprung-Russell diagram, or the HR diagram, remember, links together all of the physical features of stars in a way that pulls them all together, and each one of the dots on this is representative of a star. And if you remember from a previous video, I mentioned that all of the stars down here in this one group were stars that were dead, or in air quotes, dead. And the reason why they are dead is because these are all white dwarfs. So every one of these dots are white dwarfs that have essentially finished their evolutionary sequence. The envelope is expanded, and these are the remnant cores of what used to be intermediate mass stars. So every one of these stars down here are white dwarfs. And let me show you a couple of interesting things. If you recall, because we know the luminosity of each of these stars, and because we know the temperature of each of these stars, we can calculate the sizes of each of these stars. And if you remember, everything on this green line right here is 1/100th the size of the sun. And then, of course, as you go up, the stars get bigger and bigger. Now notice, though, each of these stars, they're about 1/100th the size of the sun. And the other thing that's 1/100th the size of the sun is the Earth. So that's how we know they're the size of the Earth, because if they are, then they're 1/100th the size of the sun. So that's kind of an interesting thing. The other thing I want to show you is, notice the specific example that is quoted on here. This one right here is called Sirius B. You'll notice way up here is Sirius A. The reason why they're both called Sirius is because it is a binary star system. Sirius A and Sirius B are companions. Now, Sirius A is a main sequence star, and it is a star that's still going through its normal life, its evolutionary sequence. It's not finished. It's still kind of going through its normal day-to-day activity as a regular star. But Sirius B is a white dwarf. And let me actually show you a picture of that. So this is a photograph. This is Sirius A. Notice it's a very bright looking main sequence star. This is one of our nearby neighboring stars. It's only about 8.5 light years away. It'll be the brightest star that you can see in the sky tonight. So Sirius A is the brightest star in the nighttime sky. But notice in this photograph, you can actually see Sirius B. So this is the white dwarf that is the companion to Sirius A, because this is a binary system where one star has finished its evolutionary sequence and has become a white dwarf, and the other star is still going through its evolutionary sequence. Now, one last little thing that goes with this is kind of cool. Because these are binary stars, companions, we know they formed together. They formed at exactly the same time from a cloud and became two different stars together as a group. But you'll notice one of them has completely finished its evolutionary sequence. Remember the rule that stars that are more massive are stars that live quicker, go through their evolutionary sequence faster. So Sirius B had to have been a star that was more massive than Sirius A for it to be completely finished with its evolutionary sequence. So even though they were born at the same time, one of them died faster than the other one because it was a different mass. Mass determines how quickly a star lives and dies. So kind of interesting. So what you can see is that a white dwarf is the remnant core of what used to be a normal star, and all intermediate mass stars will suffer this same fate. They'll puff off their outer envelope. That's the planetary nebula, leaving behind a white dwarf, the remnant core. And at this point, the star is finished. It is essentially done with its evolutionary sequence and will spend all of eternity as a white dwarf. Very slowly over time, those white dwarf stars radiate away all of their temperature, and they do steadily cool off as time goes by. And there's some interesting details related to that, but we're running a little short on time. We'll pick up those details in the next video. I hope you'll join me.